Okay, so let's continue on with this section by talking about counting sets. So what we want to discuss in this subsection is some techniques to count how many elements, how many unique elements are in a particular set. So if I give you a description of a structure, or if I give you a description of a set, can you calculate how many objects are inside? And we're going to continue with this concept by talking about probability in the next subsection. But let's begin with this. If you remember the very first example that we did in this course, it was about sum rule. And at the time, we defined a sum rule as if we had a task A and a task B, and I wanted to do task A or task B, and these tasks are mutually exclusive, then I simply just add the number of ways to do A and the number of ways to do B, and that would be our answer. Now, the assumption that's made in the sum rule is that the tasks are not done simultaneously, are mutually exclusive. But can we always make this assumption? No, we can't. We can't always make this assumption because sometimes the tasks can be done together and sometimes the tasks are not mutually exclusive. So, what do we do in those instances? So that's what we want to discuss here. We're going to get into this thing called a principle of inclusion exclusion. So the first example that I can give you is let's say that I have a bunch of courses that I'm teaching. So let's say set A is a set of courses, a set of students in my course, Computing 125. Okay, so let's say I'm teaching Computing 125 and I have a bunch of students, and set A represents my Computing 125 students. Let's say set B are Macam 101 students. Okay, so let's say that I'm teaching these two courses, and again, the set A represents Computing 125 students, set B represents Macam 101 students. What you should know here is that these two courses can be taken simultaneously, right? So that there are possibilities of students who are in both sets. So my question here is, how many total students do I have? Well, if I'm looking for the total number of students here, then I would probably guess that I'm looking for the set A intersection B. So if we just draw a very quick Venn diagram on the side here, so we have set A and we have set B. So I'm looking for the size, in fact, of A union B. So this will tell me the total number of students. Now, if I was just to follow the sum rule that I had before, I would just take the size of A and add it to the size of B. Now, would this be the right approach? Well, we could actually add these two together, but I hope you can see that on the Venn diagram. If we do that, we're actually adding this middle part two times, right? So if I add the objects that are in A to the objects that are in B, the objects that are inside are overcounted. So what we need to do is account for that. And since we've overcounted one time, I'm going to subtract what is in the middle. And the middle is represented by A intersection B. Okay, so I hope this short example gives you an idea of how to count sets if they cross over. So yes, we count the sets. We add the numbers that are in set A. We add the numbers that are in set B. But we've overcounted and we're going to subtract the overcount. This is the principle, at least the basic principle of inclusion exclusion. Because I've added too much, I'm then going to exclude, right? So I include everything and then I exclude what I've overcounted. So so this concept obviously can be extended and it could be generalized, and I'm going to talk about a little bit about how that will work a little bit later. But let's do an example here. So let's say that let's call this 52032, and I want to know how many bit strings of length 4 starts with 1 or ends with 00. Okay, Now, we see this word or here. And in the past, whenever we see a word or whenever we solve a problem using the word or, we think addition. So here we should think addition as well, but also we should note that these two things can be done together. What is a bit string, first of all? So whenever I describe a bit string, usually there is a length, oh, length four. Okay. Um, Usually there's a length that goes with it as well. So what a bit string generally means is a bunch of zeros and ones. Okay, so a bunch of zeros and ones that make up a number. Now the thing about bit strings is that they could actually start with zero. So for example, the bit string 0110 is a valid 4-bit a bit string of length 4. Okay. Now, in this question, what we're interested in is how many bit strings start with a one or ends with a zero zero. So how many of these occurs? So we're going to use this equation that we just developed in the last example here. And I'm just going to label starts with one as the set A. So all of the bit strings of length 4 that starts with 1 are going to be set A, and then ends with 0 0 is going to be the set B. All right, so again, I hope you can see that what we're looking for here is the size of A union B. So how many bit strings are in this set, A union B? So I'm just going to say this is equal to size of A plus size of B minus A intersection B. Okay, and this is always the standard equation that we're going to use when we're dealing with two sets. So what is the size of set A? Now notice that we've broken down this question, one counting question, into three separate counting questions and then have an equation that goes with it. So what's how many bit strings start with one? Well, the answer to that is that I have a one and then followed by 3 bits. Now a bit is again a character of either 0 or 1. So there's two ways to fill the first box, this two ways to fill the second box, and two ways to fill the third box. So the answer here is 2 to the 3. Right? So it already starts with a 1. The other three boxes have two ways in order to fill those. So the answer is 2 to the 3. What about B? Now, B is independent of A for now. Okay, so ends with 1 1, or sorry, ends with 0 0. That means I have two blanks, and then the last two digits is 0 0. So here the answer is 2 to the 2, right? So two ways to fill each of these boxes. And now the last question I need to answer is how many ways are there to do both? So A and B. Now, what is the question represented by A and B? Well, I want to know the number of bit strings of length 4 that starts with 1 and ends with 0 0. So starts with 1 and ends with 0 0. So you can see I only have one box to fill. There's actually 2 to the 1 here. Now, another way to illustrate this is that if I took all the bit strings that start with a 1 and then I added to all of the bit strings that end with a 0 0, then that means I've overcounted two of them. Okay, now you can verify what I said. I've overcounted two of them. So in fact, what I need to do after I add is I need to subtract this one time, and that's going to get my answer. So I think the answer here is 10. But ultimately, I want you to see how the work actually comes out to be. Now, continuing from the last example, we have a general equation for two sets. But what about three sets? Can we go a little bit further with three sets? So I'm going to draw a bigger picture here. I'm going to draw a Venn diagram involving three sets. And I'm going to see if we can sort of intuitively figure out what the equation might be. Okay, so we have set A, B, and C. All right, so if I wanted to find the size of the union of A, B, and C, the sum rule is going to tell me that you add them together. So you just take size of A plus size of B plus size of C. Now, if these sets are all disjoint from each other, right? So if this was the fact that, there's no objects in common, then this would be the answer. And from the sum rule, this would be the right answer. But let's pretend that there are some crossovers. And now the crossovers become a little bit more important because the crossovers could involve A, they could involve B, or they can involve C, any combination of them. So let's see what we have so far. This area right here, we've counted one time. When we added A, we counted this once. When we counted B, we counted this once, and then C, we counted this one. So those three areas are fine. Okay. And again, if they're disjoint, that's good. That is our answer. But notice that these areas we've counted twice, right? So for example, in this area, when I added A, I counted it once, but when I counted B, I also counted it once. And same with this area, same with this area. And then in the middle, I actually counted three times. Both when I added A, when I added C, and when I added uh, B and C, I've added one to that area. So I've overcounted that area by two times. So what should we do? Well, the next thing we should do is take the subsets that are in twos. Okay, so take the subsets that are in twos, and then I'm going to subtract off all of those. So what I mean by that is I'm going to take A intersect B, A intersect C, and then B intersect C. I take all of those and subtract them. Okay, so that is, after all, the areas that I was just referring to. Those are the problem areas, right? So if I subtract off these once each, then that means this area would now be represented only one time. I've only counted that area one time. So remember, I've subtracted the A intersect B. When I subtract A intersect C, I take one from that area. And when I subtract B intersect C, I subtract one from this area. So those three areas are now good. However, notice what happened in the middle. When I subtracted all three, I've subtracted one time from the middle. So now it's being represented 0 times. So I've actually subtracted all of them. But there's a simple answer to that because there's one last thing that we can do, which is add back the A intersect B intersect C. So this now is counted one time. So can this be generalized? The answer is yes. So the way that we're going to generalize, and we're going to talk more about this in a later section as well. But let's say we had 4 sets. Okay, so what do we do in those situations? We add the individual sets, the single sets individually. So A plus B plus C plus D, right? If there were 4 sets. And then we would subtract all the combinations that involve 2 sets. So AB, AC, BC, AD, you get the idea. So I take all of those pairs of the sets and I subtract them all. And then I add back all of those combinations with 3 sets. So ABC, ABD, ACD, and so on, right? So we add all of those back. And then finally, we subtract A and B and C and D. Okay, so I hope you can see a pattern here, right? But I hope you can also see that it gets more and more complicated the more sets that we have. Okay, so it turns out that although it is very complicated, there is a shortcut that we're going to discuss later in the course to be able to uh, to um, to analyze or to be able to calculate this number. But for now, I want you to think about this or just keep this as a formula for dealing with the union of 3 sets. All right. So the next thing that this brings us into is calculating analytic probability. So, so I just moved this to the middle a little bit. So probability is probably something that you've seen in math courses before. Maybe if you've done a statistics course, you've probably seen what probability is. But here I want to describe it with respect to set theory. So, in terms of a set, what does a probability actually represent? So, imagine that you have a universe, okay, and you have a set inside of this universe. Let's call this A. Now, this universe represents, all the possible values, right? Any possible values for this set A. And A represents a portion of it. Now, the problem with a Venn diagram, as we said before, is it really doesn't show us what the relationship is. Sorry, it does show us what the relationship is, but it doesn't show us the numbers associating with that relationship. So, for example, I don't know how big A is. Is A like really big? Does it take up a lot of the universe, or does it just take up a very small part of the universe? I'm not really sure of that. So this is what analytic probability allows us to be able to analyze. So, so assuming a likely equal likelihood, we call S a sample space. Okay, so now instead of U, I'm going to label this S. Now, the difference between U and S is, imagine U is just any object in the world. Okay, so just imagine it's like a number, or it's a positive number, it's a negative number, it's a person, it's a course, it's a school, it's a student, it's any object that you can think of. That's what U represents to us. Now, when we analyze probability, we actually use S as the universe. And what S represents is a sample space. That means it is a set of possible outcomes for an experiment. Okay, it is a possible outcomes for an experiment. So it's not just any object that we can think of. It is any object pertaining to an experiment. So, what is an experiment? Well, experiment is something that we do in order to analyze the probability. So, as an example, oh, sorry, I should probably write this here. As an example, I can say, what is the probability of rolling an even number on a dice? Okay, so we're going to assume that this is a fair dice and it's not weighted in one way or another. So the experiment is something that we do, and it is usually given in the question. So in this case, we are rolling a dice, right? That's our experiment. This is our E. Now the set S is what is the result of E. So what are all the possibilities that can happen when I roll a dice? So the S here represents the set 1, 2, 3, up to 6. Well, let's just write them all out. These are all the possibilities that I'm looking for in this experiment, that this experiment could result in. Okay. Now, there's often also a subset of S, which is called A. And A is something specific that we're interested in, which is a subset of the sample space. So in this question, it's quite obvious. It's talking about an even number, right? So even number. So the even numbers is the subset of S that I'm interested in. So in particular, A is 2, 4, and 6. Okay, so every one of the probability questions that you run into is always going to have these things. It's going to have A, which is a subset of S, which is the sample space. Okay, it's like the universe of these experiments. All right, so finally, what is the probability? So the probability, I'm going to call it PR here. You're also going to see in the notes later on that I just simplify this to be P of A. Okay, so this is represented as the probability of A. So what is the probability of A happening? It is the size of A divided by the size of S. Okay, so the size of A divided by the size of S is the probability that this happens. So in this case, the size of A is equal to 3, and the size of S is equal to 6. Okay, so we have 3 over 6, it's 1/2 probability. So So, what does probability actually measure? Well, for one thing, it measures the thing that we're looking for, the actual subset of S. How does it relate to the sample space itself? How much space does it take up of the sample space? The probability, as you could probably imagine, ranges from 0 up to 1. So any values that are close to 1, it means it is likely to happen. It is very likely to happen. It has a high probability. Whereas numbers that are closer to 0 have a lower probability. It's closer to 0. So we can argue this in the form of set theory, because what is the smallest subset of S. So it doesn't matter what S is. What is the smallest subset that I can have that is represented by A? And the answer is empty set, right? So if I'm looking for a case where it's empty, then the probability must be zero. And what is the biggest subset? Well, the biggest subset is S itself. So if I'm looking for S in the sample space of S, then the probability is one. And of course, there's every number in between that can measure the likelihood of a set happening, okay, a subset happening. Okay, so I hope you start to understand how this relates to subsets, but let's put in a little bit more examples, and let's see if we can have a better idea of how counting fits in with probability. All right, so I have a question here. We'll label this 535. Suppose there are 35 people. Let's say this is a class or something like that, and two names are drawn at random to win two identical prizes. So these two identical prizes, it should be, these two identical prizes, mm, the fact that they're identical means that you don't really care which one you win. Okay, so imagine also that in this group of people, there are two specific people called Alvin and Betty. So, what is the probability that two specific people, Alvin and Betty, are chosen, both chosen? So, I'm going to draw a very quick diagram here to represent the case of Alvin and Betty winning. Okay, so I'm going to label A, set A, as all of those cases where Alvin wins the prize, okay, independent of Betty. Okay, so Alvin wins the prize. So that means Alvin is one of the people that are chosen. So let's, in fact, yeah, so I'll just label this as set A. Okay, and then Betty will do the same thing with set B. Now, there's a couple of things that we should make sure of, first of all, and that is in this question, because we are looking for Alvin and Betty both being chosen, that we are interested in the middle here. We're interested in the intersection of A and B. Now, again, I just want to remind you that set A means that Alvin wins with somebody else, and set B means Betty wins with somebody else. Now, what we have to analyze here is what are the objects that are inside of this, inside of the universe here. Okay, so we have also an S. Now, to answer that question, I think the first thing we should do is figure out what the size of S is. Okay, now what would be the sample space? How many different outcomes can there be when I do an experiment that pulls two names out of a hat of 35? Okay, so if you want some practice, think about that. So suppose there are 35 people and there are two names drawn at random. How many outcomes are there going to be in this situation? Now, I do want to remind you that these prizes are identical. So that means that would indicate to you that this is a combination. Okay, so the answer here is actually 35, choose two, and see if you agree with that. So from the 35 names, I choose two out of a hat. And in fact, I choose these two names together, right? Because they're identical prizes. You don't care if you're chosen first or second. So the total here is 595. So if you work this out, the answer is 595. I usually don't require you to give me a number, but in this case, I want to make a point. Now, the other thing I want to show you is that what do the objects actually look like? I know that inside of this S, inside of this universe, this sample space, I have 595 objects. But what do they look like? Well, they look like two names. They look like a set of two names. Each object in there looks like a set with two names. So every object that's in A will have Alvin as one of those objects. And there's somebody else as well. All right, you can probably think what the size of A is at this point. I'll answer that question in a second. Everything in set B is going to have Betty along with somebody else. Right, so this is what these objects looks like. That's what these 595 objects look like. And of course, we have 35 names, so you can imagine all the combinations of these pairs that have two names. Okay, so the first question that we want to answer is what is the size of A intersect B? Well, at least in this case, it's actually a pretty simple question because the answer is just one. Now, please verify that you agree that the answer is one and not two, right? Because there is no there's no order, right, to which I'm grabbing these names. The one case that both Alvin and Betty wins is that one object that has both Alvin and Betty in it. Okay, so the short answer here is that the probability of A intersect B here is 1 over 595. Okay, so I hope this makes sense, that we are looking for the intersection of the two sets. Okay, the second question. Suppose there are 35 people and two names are drawn at random to win identical prizes. What is the probability that neither Alvin nor Betty win the prize? Now, I'm going to draw the same Venn diagram here. And again, A represents all the cases where Alvin wins, and B represents all the cases that Betty wins. Where is neither Alvin nor Betty? So, what does the word nor actually means? Well, it means not or. Okay, it means not or. So that means the or, the union of A and B, and then the complement is what I'm looking for. So I'm actually looking for this area right here. Now we have the same S, right? So we have the same sample space, but this time I want the case where Alvin doesn't win and Betty doesn't win. Okay, so I've already solved half of the problem from the last example. I already know the size of S, and the size of S is 595. So now we are interested in this area right here. So A intersect B, sorry, not intersect, union B, complement. So now I'm looking for this size. Now, just as an aside, I want to make a point here. If I'm looking for the if I'm looking for, let's say, a set E. Okay, I'm just going to call it a set E. And I'm looking for the complement of E. And the way that we can look for this, or the way that we can represent this, is going to be S minus size of S, sorry, minus the size of E. Okay, this is just a general equation that we can apply. Okay, so take all of S and subtract off whatever you don't want, right? That is going to give you the complement of E. So the first thing that I'm going to do here is I'm going to say that this is nothing more than the size of S minus the size of A union B. And I hope you can see that in this diagram, right? So take all of S, 595, and then subtract what the union of A and B are. Now, luckily, we have a very nice equation to figure out A union B. So A union B was size of A plus size of B minus A and B. And we discussed this earlier with inclusion and exclusion. So let's just write it like this. And now what's left is just to calculate what is the size of A, what is the size of B, and what is the size of A intersect B. Well, we have some of these answers already. First of all, we already know S is 595. We already know that A intersect B is equal to 1 because we solved that in the previous question. And now the only thing we need to answer is what is the size of A and what is the size of B? Now, if I tell you that Alvin has won the prize, who's the other person? Or better yet, how many other people can go in that slot? So again, if Alvin has already won, how many ways are there to fill this box right here? Okay, the answer to that is 34, right? It could be Alvin with any of the 34 remaining people. What about Betty? If Betty wins, how many other people can win? The answer is also 34. And I hope you can see that if I add 34 with 34, there is one overcount, which is the case where both Alvin and Betty wins. So I subtract that off. So hence we have the inclusion exclusion formula, and I think this is going to give me 528 if my calculation is correct. Okay, so ultimately the solution here is the probability of A union B complement is equal to A union B complement over the size of S, which is 528 divided by 595. All right, so I hope from this example, you're able to see how inclusion exclusion plays a role sometimes in probability. We can actually apply this law, these inclusion exclusion laws, to probability as well. Now, even though I used the inclusion exclusion law in this problem, I just want you to see that, in fact, I didn't really need to. I didn't really need to use the inclusion exclusion law. If I want to answer this question again, what is the probability that neither Alvin nor Betty win the prize? I don't want either of them to win the prize. So, another way to say this is that maybe they're not part of the discussion at all. So, understand that one other way that I could have gotten the answer to 528 is that this could have just been 33, choose two. So I just take Alvin and Betty and just remove them from the set of people. This is very much like the way that we did the proof of Pascal's theorem last week or last video. So just verify that 33 choose 2 is actually another way that we could have gotten 528 as an answer, but I wanted to use this opportunity to show you inclusion exclusion. Okay. All right. Next example. Let's say that we're counting cards, and this is a poker hand. And if you're not sure what a poker hand is, let me just introduce you to cards. So what a playing card is that we have numbers, and let's call this call this set n. Okay, so numbers, and these numbers range from a to 3 all the way up to 10, and then there's a j, there's a q, and there's a k. So jack, queen, and king. There's also a size S, which is the suits. So the suits are the diamonds, the hearts, the uh, spades, I believe, and then the clubs. Okay, so we have four suits. And what a playing card is, or what a deck of playing cards is essentially n times s. So playing cards are represented by the set n cross z. Now, if you remember what crossing means, it means I take one object from the first set and then I cross it with an object from the second set, and I want all such crossings. Okay. So ultimately, the number of playing cards that I have is going to be the size of n cross z, which in this case is 13. So 13 numbers times 4, which is 52. Okay, so I have 52 playing cards. There's no jokers here. Okay, so what I'm interested in is if we're playing poker and I randomly give you 5 cards, what is the probability that you're going to receive exactly one pair? Okay, what is exactly one pair? So I'll give you an example. These cards come with a number as well as a suit. Okay, so let's say I give you 5 cards: one, two, three, four, and five. Okay, what one pair means is that two of these cards have the same number. So, for example, let's say I give you a two of heart and I also give you a two of diamond. And then the other cards, let's say, are four, five, and eight, something like that. Okay, so four could be anything, five could be anything, eight could be anything. Right. So this is a situation where you have exactly one pair. So exactly one pair means that I don't have another pair in the other cards, and I don't have a triple as well. So I don't have three twos, and I also don't have another pair aside from the twos. Okay, I hope that makes sense. So exactly one means exactly one, right? Nothing more, nothing less. So, by the way, if you get this in poker, I think you should throw it away. It's a really bad hand. Um, so, anyways, what is the probability given a 5 card hand that I'm going to receive exactly one pair? All right. So the first thing we'll do is answer I guess, the easier question, which is what is the size of S? So how many different outcomes can I get with a 5 card hand? So, well, we have 52 cards, and I'm randomly giving you 5 cards. Now, ask yourself this question: does it have order? Do these cards have order? And I don't think they do because I can randomly give you five cards and the order in which I give them to you will not matter. So I think the answer here is 52 choose five. Okay, 52 choose five for the total number of ways that I can give you five cards from 52. Now, what is the S that I'm looking for here? Well, it's the exactly one pair. Okay, so A represents, so let's pretend exactly one pair is represented by set A. What is the size of A here? Well, that's a little bit difficult of a question, but I think what we should do is break this down into two parts. So you notice that whenever I have exactly one pair, that I have a pair, so I have two cards that have the same number, and then I also have three, we'll call them singles. Okay, so these are the pairs, and these are the singles. All right, so the question is if I wanted to get the pairs, if I wanted to know what the pairs are, how many of the pairs are there? Well, I'm going to break that question up into two parts. First, I'm going to answer how many ways are there to fill the numbers? Okay, well, since there are 13 numbers, it must be 13 choose one. Okay, so if I take from the 13, if I take from the set n, and I'm going to grab grab one of those numbers from 13, then I could fill it into that pair slot. Okay, so let's say I choose the number 2, and 2 would be filled into that slot. Okay, now notice it's the same number. All right. The second thing is that how many ways are there to fill the suits? Well, we have 4 suits, and I have to choose 2 of the suits to be here. Right. So I have 4 suits, and I need to choose 2 of the suits to be in those playing cards. So here we're going to do a 4 choose 2. Now, please understand why it's choose, because if it's a pair, again, the order does not matter, right? So if I pick a heart and then a diamond, it's the same as diamond and then heart, right? So there is no order here. All right, so again, this represents how many possible pairs there can be. What about the singles? Well, we're going to go through the same process with the singles. For the numbers, we have 12 numbers remaining. Okay, so after we've chosen the pair, we have 12 numbers remaining. Remember what I said, the singles cannot also be a 2, right? So I can't have a 2 in there. That would make it a triple. So 12, and I'm going to choose 3 different numbers. So 3 different numbers to put them there. So for example, I can choose 4, 6, and 8. 4, 5, and 8, whatever I said before. So whatever is chosen, that is where you're going to put it in in each of those slots. And once again, the order doesn't matter, right? So I could have given you 6 and then 8 and then 4. It doesn't matter. Okay, now after I've chosen each of these numbers will have a suit associated with them. And I just want you to see that when I fill these suits, they can be anything, right? They can be any of the 4 suits that we have. So for the 4, we have 4 choose 1. For the 6, we have 4 choose 1. And then for the 8, we have 4 choose 1. Okay, so in essence, in order to choose the suits that go into each one of those numbers, the answer is 4 to the power of 3. So the number of remaining singles that we can choose is 4 to the power of 3. Okay, now I hope you followed that logic, but essentially what I did was, even though this was a pretty long question, I've broken down into product rules, right? So remember product rules from week 1. So I have pairs and singles. For a pair, I have the number and the suits, right? So I've broken them down into logical steps that I can solve individually. So the number of singles, or pairs, exact pairs, is 13 choose 1, 4 choose 2, and then 12 choose 3, and then 4 choose 1 3 times. Now, the probability of A happening is going to be the size of A divided by the size of S. So here we have the solution. Now, I'm just going to give you the exact numbers here. You can calculate the percentages if you're interested in doing poker professionally. You can calculate these numbers. think it's about 40% that we can get exactly one pair. So just verify those numbers. By the way, if you want a little bit more practice, go to like a poker.com site or something like that, and they usually give you the probability of all of these. So the poker hands, if you look in the textbook, you have a lot of practice questions on those. But poker hands are things like exactly one pair, exactly one triple, four four of the same card. There are these special hands as well called full house, straight, flush. You should look up the definition for each one of these, and there are some examples that are given to you in the textbook as well. So practice those. Those are actually pretty good questions for an exam or something like that. Okay, so that's the application for poker hands, and let's do one more just so that we understand everything for basic um, probability. Now, I did have an example here on trees. I'm just going to skip over that. But I'm going to do one last application here. And this application you should be able to do with the tools that you have right now. So if you want to challenge, you can pause the video here. You know, we'll treat it like an in-class assignment and see if you can answer this question. All right, I'm going to randomly rearrange the words letters. What is the probability that the arrangement contains either EE or TT? Okay, what is the probability that the arrangement contains either EE or TT? So meaning that they are stuck together, right? The EE or the TT are stuck together. Okay, so again, we have an experiment. The experiment is rearranging the letters, and I'm going to start with the size of S. So how many total ways are there to rearrange the letters? Letters, right? So here, I hope everyone is able to answer me this question. So 1, 2, 3, 4, 5, 6, 7. We have 7 factorial. And you remember, if there are repeated letters, we have to divide them off factorial. So we get 2 factorial for the E and the T's. Okay, no other letter repeats. So I think this is our S. This is our sample space. All right. So now let's label the case where you have 2 consecutive E's. Let's label this set E, and let's label this one set T. Okay, so set E is the case where 2 E's are together, and the set T is the case where 2 T's are together. I am essentially looking for the size of E or T, E union T. And again, we have this equation, size of E minus, plus size of T minus E and T. Okay, so eventually I'm going to have to solve this probability. I'm looking for the probability that the E union T, the probability of E union T. All right, so what is the size of T, size of E here? Size of E, imagine that we have 2 E's already together. This is one object. So aside from this, we have another T, we have another T, we have L, we have R, we have S. So altogether, we have 6 objects. Right, so we have 6 objects, so 6 factorial. Do any of these objects repeat? Well, the 2T's repeat. So I'm going to divide 2 factorial. Now notice the E's do not need to be switched or anything like that, because the 2 E's is understood as one object here, right? So this is, once again, the set E represents all of those cases that have 2 E's adjacent, all of the rearrangements that have 2 E's adjacent. All right, what about the size of T? Well, the size of T is the same argument, except instead of the 2E's being one object, the 2T's are now one object. So again, we have 6 factorial over 2 factorial. And finally, what about E and T? So E and T is talking about the case where both E's are together and both T's are together. So we have this case, and you see that we have 5 objects and none of them repeat. So I have this as our solution. All right, so finally, what is the probability of E union T It is the size of E union T over the size of S. So here we have the answer 6 factorial over 2 factorial plus 6 factorial over 2 factorial plus, sorry, minus 5 factorial, and then finally divided by 7 factorial over 2, 2, and 2, or over 2 and 2. So again, if this was a quiz or anything like that, I would prefer not I would prefer just to have this equation, right? So just represent your answer in this equation rather than a specific number, right? Okay, so I hope you have a pretty good idea of how basic probability works. We're going to talk in the next video about some more advanced topics in probability. But if you were having trouble understanding this, again, I invite you to go back and take a look at the video again. So in particular, I want to stress the fact that whenever you see a probability question, the first thing we need to do is identify what is the experiment. Okay, so what is the experiment? What are we doing? And then what is the S? What is the sample space? How many different outcomes are there from this experiment? Okay, that would be the size of S. So you notice that in every one of these examples, that's what we did. Thirdly, I want to figure out what the subset is. What is the subset of S that I am looking for? Okay, so if you find that your set, the set that is like the set A that we said before, is not part of the subset of the sample space, then you might have it wrong. Okay, so just analyze that whenever you do a application on probability. Okay, so I'm going to stop the video here, and when we come back, we're going to talk a little bit more about more advanced topics in probability.